let's go to the third use case. And this one is really, I think, fascinating for me because this incorporates this concept of taking a quantum network and making it a wide area network. There's a lot of local area network models that are out there and metro area networks. But as you go to a wide area network with larger geographical distances, it might be in a regional location, maybe it's in a single country, maybe it's on a continent, maybe even be potentially globally. In those cases, we need something like a repeater, similar to a router in the classical networking sense, a repeater that we can place in between Alice and Bob. It seems like Alice and Bob keep showing up everywhere we go. And these repeaters allow us to extend the distance. Now, from what I understand, there are no commercially available repeaters. I think there's a lot of development going on in this space, as there is with memories. And I know from the repeater perspective, you've got to have memories in the repeaters, at least in terms of this implementation, to be able to create a repeater. And I think there's got to be 2 memories there in each repeater. So can you talk to us a bit about this? And I think this use case for me is really all about taking the applications and the use cases we've talked about and extending them over a large geographical area, which ultimately over time is going to be necessary for quantum networks to really scale. Talk to us a bit about this model and the topology, the architecture, and your approach to this, please.
Sure, Mike. So as you mentioned, we are going to try, to achieve end-to-end entanglement between Alice and Bob, but this time Alice and Bob are way too far apart. Like they're not close as before. So as you said, we are going to be needing repeaters to actually extend this entanglement over, this long distance. So, in the screen we can see, kind of the setup that you've been describing. We have Alice and Bob and our 3 repeaters in the middle, and so this is going to go a little bit, like this. So first, we're going to have to perform elementary entanglement between each pair of neighbor nodes. So you see here, like this red line, representing an elementary entanglement between Alice's qubit and one of the qubits in repeater 1, and the same for the other, pairs of nodes, right? We see here entanglement between repeater 1, a qubit in repeater 1 and a qubit in repeater 2, and then the same for repeater 2 and 3 and repeater 3 and Bob. So the first thing we need to do is we need to achieve those 4 elementary entanglements before we go to the next step. So it's important to note here that it really doesn't matter which elementary entanglement we reach first. We could be, reaching elementary entanglement between Bob and repeater 3 first, before Alice and repeater 1, but this doesn't really matter in our protocol. So after we have these 4 elementary entanglements, we're going to be looking at a swapping operation in the repeater 1. And so this is going to be extending the distance of our entanglement, and we're going to end up with Alice and repeater 2 being entangled, which is great because repeater 2 is actually closer to Bob. And then the same procedure repeats itself for the other half of the network. We see that we have a swap operation on repeater 3, and that is going to be extending our entanglement and we're going to get Bob and repeater 2 entangled. And then when we have this, at this stage in the protocol, the final step is to actually apply a swap operation at repeater 2, so we can finally end up with our end-to-end entanglement, which is our goal. So, and also in this protocol, it doesn't matter which swap occurs first. We can swap first here in the repeater 3, and then swap again, and swap then on the repeater 1, and it doesn't really matter. So this is what our network looks like. This is what we're going to be seeing in the protocol. So let's go to our script and run the simulation and see what we get.
Yeah, I'm excited to see this, Michelle. This is pretty complicated and pretty sophisticated. I can't imagine how one would actually design and simulate and begin to analyze this without some level of simplified visualization. The other factor here that I'm observing is that, again, we still have the fiber optic parameters that we're going to have to incorporate. We're going to have to get feedback from the telco carrier on that and profiles for the fiber optic cables. We still have Alice and Bob again, and their factors around memories and things like that. But then now we've also got the repeaters, and they're going to have their own parameters and characteristics. And we theoretically would go to the vendor and say, what are the parameters for your 7 types of repeaters that you offer, the 2 types of repeaters you offer, and go to each vendor and compare those and enter those parameters in. There might be a cost variation, of course, depending on the type of quality that we're looking for within each of the repeaters. So I'm looking forward to seeing how you walk us through this configuration and what the outcome looks like.
Alrighty, let's go ahead and do that. And yes, you're right, Mike. What we're going to be doing now is we're going to again be, giving our simulation a set of parameters, and we're going to be doing this a little bit different this time. We're going to be passing the parameters directly in the command that we're going to be executing to run our simulation. So let's take a look at what those parameters look like. So, all right, our first, start running our, selecting our script to run, and then we're gonna tell it that we're gonna be running this, that our network is gonna have 5 nodes. So we specify that in the command, and then we're going to be specifying a coherence time for each of the quantum memories in our network. So in this network, we have 5 nodes, and 3 of those nodes are repeaters that contain 2 memories each. So in total, we're looking at 8 quantum memories. So let's specify a coherence time for each of those 8 memories. And we're going to be using 1 millisecond for each of these memories for the first simulation, right? So 1 millisecond, 2, 3, 4, 5, 6, 7, 8 quantum memories. Okay, so these are the parameters for coherence time. And then we're also going to be simulating the performance of our repeater. And the way we're going to be doing this in this example is we're going to be providing a probability that a swapping is successful for each of the repeaters. So we're going to be, let's start with a 40% success probability for the swaps. So let's say that 0.4 for each of the repeaters. And then finally, we're going to be telling our script that our nodes are going to be separated by 5 kilometers. So 5 kilometers for our 4 distances. And then, we need to add, 2 more arguments to our command so we can run our simulation. So let's go ahead and do that. And finally, we need to tell it, as we did in the previous examples, we're going to have to tell it where we want to store our log file that describes what happened in our simulation. So we're going to go ahead and find a good place to save this and give a name to the log file. So why don't we call this repchain1.log, and we're ready to run our simulation and see the results we got using this different parameters. So our simulation already ran, and if we go to our visualizer, we can again repeat the process of providing a network configuration file, the log file, I believe it's this one, repchain1, let me just check, yes, repchain1.log, and then we hit visualize. Let's zoom in a little bit and scroll down to see what this visualization is going to be displaying. So we first see that we have our 5 nodes. Alice and Bob are nodes 1 and 5, and our 3 repeaters are nodes 2, 3, and 4. So, in this simulation, a lot of things are happening that didn't actually happen in the previous examples because we were running, less complex protocols. But this is a more complex protocol. So this is where we see the usefulness of the visualizer even more. Because, for example, we here are seeing that, the nodes are talking to each other to tell them, oh, we had to start the protocol. So, this is what's happening at the beginning of this simulation. And then if we keep scrolling down, when they all have started their protocols, we begin to see the elementary entanglements we were talking about between each pair of neighbor nodes. So here we have our elementary entanglement with these two repeaters. Here we have our elementary entanglement between repeater 3 and Bob, etc. So if we keep scrolling down, what we're expecting to see is, swapping operations to achieve entanglement, to extend entanglements. So, but yeah, this time we're seeing a lot of failures, and we are also seeing how nodes are being communicating these failures. So, what do you think about this so far, Mike?
I think it looks pretty bad. I mean, it's great. It does seem like one thing, the entanglement is happening between each of the nodes, which is great. It appears as though we see a swap success there, but a lot of the other swaps have failed. And I'm wondering, I know you picked up parameters from the data sheet that we had for this repeater, again, once they eventually become available, and the swap probability was 40% with that particular selection. I'm wondering if we could actually, maybe that's a good repeater, if we could go to a better repeater that has a better swap, probability of swap, or maybe even a best repeater that's got kind of the gold standard of swap probability. Can we upgrade that, pull the specs from that better repeater, and load those into the simulation and run this again?
Yes, for sure.